So we're working our way through circle theorems. This time we're going to prove the tangents from an external point theorem. All right, so this is a circle theorem, so I'm going to need a circle. Okay, there's my circle with a center in it. Now I'm going to put a point over here, external point. So this is an external point. And then it says tangents from an external point. So if I draw a line from that point to the circle so that it forms a tangent with the circle, just touching it, what I'm going to get is a tangent that looks like that, heading off into space like that, and a tangent that looks like that. Now, what the tangents from an external point theorem states is that the tangents from an external point are congruent. They have the same length. So the theorem states that AC is congruent to three lines CB. They have the same length. So I'm not going to draw this little thing in here because I don't know that yet. That's what I'm trying to prove. Now, you might want to pause it at this point and try to prove it yourself. Otherwise, I'm going to get started. So as is so often the case with these things, it's a good idea to start constructing some lines, drawing some lines where you think they might make sense. And here's my external point, here's my origin. I want to create some triangles. And I can do that by constructing a line OC. I can do that by constructing a line OA. And I can do that by constructing a line OB. So what do I have now? I have this triangle here, and I have this triangle here, and I'd say my drawing's pretty good. And you might say to yourself, they look like very similar triangles. Maybe they're even congruent triangles. And if they were congruent triangles, that means that this length would be equal to that length, and I would be finished. I would have solved this thing. So let's go about trying to prove that those two triangles are congruent. How can we do that? Well, OC is a common side, right? Both triangles have a line OC. This one and this one both have OC. So I'm just going to write that OC is common. Now, what else can I see? All right, well, this side here is interesting, and this side here is interesting. In fact, they're so interesting that they're equal because they're both radii. So I can say that OA is congruent to OB because they're both radii. Now, why am I using this congruent sign? Well, when we're talking about lengths of things, we can say that the lines are congruent. They are the same length. Just a clever way of talking about geometric things instead of numbers. Now, what else have I got? I know this length, I know this length, this length. Now, I'm trying to prove that these are equal. Now, you might start thinking like, well, if that's equal and that's equal, then like Pythagoras' theorem. But I can't use Pythagoras' theorem because I don't know that these are right-angled triangles. Or do I? Because this one here, this is a tangent and this is a radius, and we've used that before, so we can now say that that is a right angle and that is a right angle. So I can say that angle OAC and angle OBC are 90 degrees. And the reason I can say that they're 90 degrees is because of my tangent theorem. Now, if you're comfortable with congruent triangles, this is where our proof comes to an end, because we can say that OAC is congruent, that's triangle OAC, triangle OAC is congruent to OBC, and the reason that they're congruent is RHS. A right-hand triangle with a hypotenuse and a side. A right angle triangle with a hypotenuse and a side. A right angle triangle with a hypotenuse and a side. Now, if they are congruent, therefore line AC is congruent to line CB, and that's what our theorem states, and we can say that it's proven. Now, that's where we might like to stop, but a lot of people don't like congruent triangles. They kind of freak them out. So we could ignore this bit for a second and use a similar thing that we've done before where we essentially employed Pythagoras' theorem at this stage. Because on this bottom triangle, so pretending this didn't happen at all, we can move on and we can say, well, this is my right angle, so that's my hypotenuse. So I can say that OC squared equals, I'll work with the bottom triangle first, OB squared plus BC squared. Okay, and I can also say that OC squared equals, what should I use first? Try to line things up. OA plus AC squared. All right, so I have two of these. Now, what can I do with that? Well, I could say that these are equal to each other, right? That's probably a pretty good way to go. All right, so this equals OC squared, so we can put that here. And this equals OC squared, so they must be equal. And then take a look at here. We know that OA equals OB, so OB squared equals OA squared. So we can cancel these out because they're equal, and therefore BC squared equals AC squared, and we can finish now by saying that BC equals AC, and I suppose we should say that they're congruent, and then that's proven. So a little more work there, but it avoids having to use our little congruent triangles if that's something you're not super excited about. All right, so obviously now that you know that from an external point, you can find two tangents that will be equal to each other.